Okay, I wanted to just go back to what we just finished in the last video, and that is this Taylor series. It's a Maclaurin series, of course, Taylor series with centered about zero is called the Maclaurin series, but it's a power series representation for the function e to the x. And I just want to say this, that the whole process of finding this Taylor series, this power series representation for a function, was solely built upon what? Finding the value of the function and its derivatives, the first derivative, second derivative, third derivative, and so on, only at the value of x equals 0. Okay. Now the book goes into much more detail about this, but the question becomes, okay, we know that this function behaves, this power series I should say, behaves exactly like the original function e to the x, where? At 0, right? Clearly it happens at 0 because we're forcing that, right? We're forcing this function to behave exactly, or this power series to behave exactly as e to the x at x equals 0. But the question is, what about for values of x not equal to 0? The domain of the e to the x function is all real numbers. Also, this power series, you can go back in our videos, we showed this power series has an infinite interval of convergence. When we first looked at power series, we looked at this one. And so its radius of convergence is infinite. It's convergent for all real numbers. This power series for any value of x, if x is 0, 10, negative 50, 1000, whatever, this power series is convergent. So the question becomes, is this power series indeed converging to the values of e to the x? And there's a little bit more mathy work to be done there in proving that. I just wanted to look at this from a little bit of a geometric perspective. I want to take a look at the graph of e to the x, and I want to take a look at the graph of this power series. Obviously I can't enter in all these terms because how many are there? Dot, 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 right? It goes on forever, right? It's an infinite series. But we can approximate. So I'm going to start with our function e to the x. I'm going to graph it, and then I'm going to graph this Maclaurin series. I'm just going to start with one term and then build up, just add another term. So my first term is just 1, okay? And I'm going to graph the Maclaurin series as a solid or a thick line, and the e to the x is a thin line. So when I look at the graph, here's e to the x. This is y equal 1, right? Just 1. How good of an approximation do we have to the graph of e to the x? Pretty bad. The only thing we have is what? They share this point in common. That's not very good, okay? Now, when I go to adding plus x, this term, what is that added to things? Well, let's take a look now at the graph, right? There's e to the x. Now our line has, right, slope 1, right? We share the same point right there, but what else do we share? This is the tangent line to the graph of e to the x at 0. So not only do we have the value of the function equal at this point, the derivative, right, the first derivative is equal at this point, right? Okay. Now let's, and it's still not a very good approximation though. Now let's go to the third term, which is x squared divided by 2 factorial. 2 factorial is 2. So I'm just going to do x squared divided by 2. And now let's see what happens. Okay. All right, so it's a quadratic function. Now take a look at it, right? It kind of curves in there. So now we have what? We have the value of the function is the same, the derivative the same, and the second derivative, which if you remember talks about concavity, right? So we're concave up in that region. But right, the solid curve now, kind of right in here, it almost merges almost with e to the x. Now if we zoom in real close, we'll see there's still some slight difference, but it's doing a pretty good approximation in there. Okay, let's do one more term. What's the next term going to be? X cubed divided by 3 factorial. All right, and x 3 factorial is 3 times 2 times 1 is 6. So this is x cubed divided by 6. All right, let's take a look at the graph now. There's our e to the x, and look at that. It's still bad here, right? We're going down, right? This is a cubic function now. It's like a cubic function, right? It's going down to minus infinity as x goes to infinity, whereas the e to the x function has a horizontal asymptote of y equals 0. And here they're both going to infinity. But do you see how it's getting a little bit closer? Let's go to the fourth term, which is plus x to the fourth divided by 4 factorial, which is 24. There's our function, and there's the approximation. Do you get the feel for what's happening here? And it is indeed true that in this case, this power series converges to e to the x for all values of x. By converge, I mean, right, as n goes to infinity, right, we look at this actual sum. This power series is convergent for any value of x, and its sum is equal to e to the x. And that's a powerful thing. So that's what's going on with these power series representations. They're doing a very good job. Now, if I go back out here, let's just open this window up a little bit to x equal -4. Right? If I go back far enough, you see my polynomial, my e to the x is here, and our power series is converging to something over here. So they're well, it's not converging. I'm just adding first few terms, but right, there's certainly a gap here. Okay, but if I'm approximating a value of e to the x near x equals 0, I'm pretty darn well good just to plug in the value of x right here, and I'll get a pretty good approximation. Right, for any value, you know, close to 0, like -0.2 to +0.2. But if I'm back here at -2, you know, -2.1, 2.3, or something like that somewhere else, there's a pretty big discrepancy there. Okay, so that's where the being centered about matters. This was centered about 0, so it does a good job close to 0. If I want to do a Taylor series for e to the x centered about x equal -2, I will do a better job of being convergent close to -2 very, very quickly with just adding a few finite terms. Okay, so where we converge about, where we're centered about, also matters. Let's take a look at a Taylor series now where we're centered about somewhere other than 0. Let's find the Taylor series for this function centered about a equal 1. Okay, so remember our Taylor series is this. It's the nth derivative evaluated at a, and a in this case is 1 over n factorial x minus a, which is 1 to the n. So I just need to figure out what this thing is so I can express this in a formula of a function of n. What is the nth derivative evaluated at 1 for this particular function? Okay, so we start, remember, with the 0th derivative, which was the function itself. That is just 1 over x. And then, of course, I'm interested in evaluating that 0th derivative at where? 1, right? We're centering about 1 this time, right? So that's 1 divided by 1. That's a big fat 1, right? What about the first derivative of the function? Well, what is the derivative of 1 over x? Well, 1 over x is what? X to the -1 power. X to the -1 power. So that's negative x to the -2, or -1 divided by x squared. So the first derivative evaluated at 1 is going to be -1 divided by 1 squared is -1. So we got 1, we got -1. Second derivative. So this is negative x to the -2. Negative x to the -2. So bring the -2 down, what happens? -2 times that -1, what happens? +2. X to what? -3. Subtract 1 from -2. I get +2 x to the -3, or 2 divided by x cubed. Okay, this is 2 times, again, this is 2 times x to the -3. Right? So this was negative x to the -2. Bring the negative down, makes it +2. Subtract 1 by the power rule. So I'm going to use this form here to deduce that the second derivative evaluated at 1 is 2. 2 divided by 1 cubed is 2. What's the third derivative going to be? Bring the -3 down. I get -6 x to what? Subtract 1, negative 4. I get negative 6 to negative 4. I'm looking for a pattern here, though. I'm looking for a pattern here. So instead of negative 6, I'm going to write this as negative what? 3 times 2. And it was what? X to the negative 4, which becomes over x to the 4. I'm looking for a pattern. So it's very helpful to sort of leave this unmultiplied, so to speak, up top. What do I get, though? Of course, I get negative 6, right? But I'm going to say negative, I'm going to say negative 3 times 2 times, well, isn't that the same as 3 factorial? Isn't that 3, I could put a 1 up there if I want to. It doesn't change anything. That's 3 factorial, negative 3 factorial, negative 6. It's negative 6, but again, I'm thinking of a pattern here. And I think you'll see this pattern develop. Let's do a couple more. This will be what? X to the negative 4 comes down, so negative times negative makes it positive 4 times 3 times 2. Of course, that's going to be 24. X to the negative 5, so 1 over x to the 5th. So our fourth derivative, evaluated at 1, is going to be, 4 times 3 times 2, 4 factorial. Right? Which is 24, yes, but I want to put it in that form. The fifth derivative, this is what? 4 times 3 times 2, x to the negative 5, bring the negative 5 down, it becomes negative 5 times 4 times 3 times 2 over x to the 6th. And this is negative what? 5 factorial when I plug in x as 1. All right. Do you see a pattern here? Now you certainly see a pattern, certainly down here, but does this pattern work? Yeah, because this is the same as 2 factorial. This is the same as negative 1 factorial. And this is the same as 0 factorial. If you remember, 0 factorial is defined to be 1. 1 factorial is also 1, so this is negative 1. Do you see it? 0 factorial, negative 1 factorial. 2 factorial, negative 3 factorial. 4 factorial, negative 5 factorial. What's the next one going to be? 6 factorial, right? Then what? Negative 7 factorial. So you see the pattern. And the question is, how do I write that out? In other words, what is the nth derivative, right, evaluated at 1? Okay. Well, obviously, when it's 0, I get 0 factorial, 1, it's 1 factorial, 2, 2 factorial, 3, 3 factorial, so on. So it's definitely n factorial. But what about the sign change? Do you see that? Positive, negative, positive, negative, positive, negative. We need a sign changer. Do you remember how we get sign changers in our series? What were they in our power series? Negative 1 to some power n, right? And I'm going to say it's going to work when I do n. If it doesn't work, I could do n plus 1. I'll explain that in a minute. But notice when n is 0, negative 1 to the 0 power is positive 1, so I get 0 factorial. When n is 1, I get negative 1 times 1 factorial. When n is 2, I get negative 1 squared is positive 1, 2 factorial. When n is 3, I get negative 3 factorial. When n is 4, I get 4 factorial. You see, that's the sign changer I need. If it was, if it was negative 0 factorial, positive 1 factorial, negative 2 factorial, positive 3 factorial, then I can do something like negative 1 to the n plus 1 here. And that would do the sign changing for that sequence. Well, there it is. And now we have a power series representation for the function 1 over x centered about a equal 1. Here it is. I'm just going to replace the fn, the nth derivative evaluated at 1, with negative 1 to the n times n factorial. So this is up top. Right? This is up top, right? Over what? N factorial x minus 1 to the n. But what happens? Can you simplify this formula? Can you simplify this? Yeah, what happens here? Right? N factorial, right? And I'm left with this as our power series representation. Oops, I forgot my n up here, didn't I? That's not changing signs anymore, right? So we need to make sure we include that. So it's negative 1 to the n times x minus 1 to the n. And we actually, if you go back in the power series video, we actually derived the power series for 1 over x. We did it a little differently, though. We did it a little differently. But this is the same power series we got. And this is a direct way to find it. But you do have to find the pattern. Okay. Now, the examples we've seen so far, this one's still pretty easy. In general, that pattern can be quite difficult to deduce. Okay. Now, what we can do sometimes as far as homework problems go, or test questions or something, instead of seeing a pattern, I can just ask you to give me the first 4 terms of the Taylor series. So you would just go through and find, this, the first 4 terms down to here, and you would just plug in to the formula, and you would just list them out, right? In other words, going back to our example for the Maclaurin series, if I asked you to write the first 4 terms of the Maclaurin series for e to the x, you would just have 1 plus x squared divided by 2 plus x cubed divided by 6, and then you could stop there, But in general, if you're going to find the Taylor or Maclaurin series, you have to find the pattern of the nth derivative of the function evaluated at a. And we're going to do that again for sine and cosine. Let's find the Maclaurin series. All right, again, Maclaurin series means we're centered about a equals 0. And I'm going to do it for sine of x, and then I'm just going to give it to you for cosine of x, but the way we do it will be pretty obvious. So f of x is sine of x is our function. That's f of 0. And so f of 0 evaluated at 0 is what? Sine of 0 is what? That's 0. F prime of x is cosine of x. Therefore, f first derivative evaluated at 0 is cosine of 0, which is 1. What's the second derivative? It's derivative of cosine of x, negative sine of x. So that means f second derivative evaluated at 0 will be minus sine of 0, but sine of 0 is 0, so I still get 0. Third derivative of negative sine of x and negative cosine of x. So the third derivative evaluated at 0 is negative cosine of 0. That's negative 1. And the fourth derivative, what's the derivative of negative cosine x? That's sine of x. Of course, we're back to 0. But sine of x means we're right back here. And what's going to happen when I take the fifth derivative? I'm going to get cosine of x. And so the pattern's going to repeat. I've got the pattern, right? What's the fifth derivative at 0 going to be? It's going to be 1. The sixth derivative going to be 0. The seventh derivative going to be negative 1, right? This pattern continues, right? What is that pattern? Well, not necessarily the coefficients, but really when I say the pattern of the fn evaluated at 0 is what I really mean. It's not really the coefficients, because the coefficients are divided by n factorial. But at any rate, you see the pattern. What is it? 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1. Right. That's the continuing pattern, right? All right, so now we're ready to actually get the answer. I'm going to write it out here. Our Taylor series, or Maclaurin series again, because we're centered about 0, for sine of x, right? Okay, what's the first term going to be? Well, this fn of 0 is going to be what? 0. 0. Right? And then what? It's going to be 1, right? Over 1 factorial. 1 factorial is 1. X to the first is x. I just get an x. Plus what? The third one. N is 2 in this case, right? That's our third 1, because we're starting at 0, right? So this is n is 0, n is 1, n is 2. But that's the third one in this list. It's 0 again, right? So it's alternating. The next one's going to be what? Negative, right? So that's going to be a negative what when n is equal to 0, 1, 2, 3 now, right? So I get 3 factorial x cubed. So this is plus a negative x to the third power over 3 factorial. Plus what? 0 again. Plus what? Back to positive 1. 3, 4, 5. This will be what? X to the 5th over 5 factorial. Plus what? 0. And then what? Minus x to the what? 7th over 7 factorial. And that goes on and on and on. But what's the real pattern? Let's get rid of the zeros. And what do we have? We have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Do you see the pattern? What's next? Plus what? X to what? The 9th over 9 factorial. Minus what? X to the 11th over 11 factorial. Right? There it is. Can you write this out compactly now? Well, it takes a little bit of a trick here. I certainly see that I have a sign changer, right? The first term is positive, then negative, positive, then negative, positive, then negative. So in this way, I can just write that as negative 1 to the n, because when n is 0, I get positive. When n is 0, I get positive 1. When n is 1, I get negative 1. When n is 2, negative 1 squared, I get positive, and so on. But what about the top? What is the exponent here? What is the exponent? The exponent's 1, 3, 5, 7, 9, 11. What are those? Odd numbers. How do I get odd numbers out of this? Well, even numbers is easy, right? You just double, right? If I do 2n, when n is 0, I get 0. When n is 1, I get 2. When n is 2, I get 4. When n is 3, I get 6. So 2n gives me that. How do I get to the odd numbers from 2n? Just add 1 in this case. Notice when n is 0, what do I get? 2 times 0 is 0, plus 1, I get 1. Right there. When n is 1, what do I get? 2 plus 1 is what? 3. When n is 2, 2 times 2, 4 plus 1, 5. When n is 3, I get 7. When n is 4, I get 9. When n is 5, I get 11. That's how I do it. Well, what's the bottom going to be? What factorial? What's the odd numbers, right? Odd numbers. So it's what? 2n plus 1 in parentheses factorial. This is the Maclaurin series for sine. In a similar way, I'm not going to do all the derivation, but you can imagine it will look very similar because of the way these derivatives work. The Maclaurin series for cosine of x would be x to the 2n over 2n factorial. So basically, instead of the odd powers of x, it will be the even powers of x. So there they are. There they are. And you can do the same thing that I just did a minute ago with the e to the x function. These will converge very nicely to sine and cosine near what? These are Maclaurin series near what? Near x equals 0. Right? But as you add more and more terms, they begin to get closer and closer to the sine and cosine function. And you may want to try and do that. Just, do maybe the first several terms of this series, graph that versus sine of x, and just compare. And maybe add another term and see how that's getting closer, if you will, converging to. Again, both of these power series are convergent for all real numbers. Their interval of convergence is infinite. And indeed, it is true that both power series converge to sine of x and cosine of x respectively for all values of x. So again, very powerful. Okay, so We've looked at some examples. You can look in the book in chapter 10, section 7, and it will show the power series representations for several different types of functions, including these ones that we have developed here. What I'm going to do is using that as a basis, how do we create the Taylor series or power series representations for other functions? So we'll look at that in the next video.